Okay. Okay, so the title is From Constant Mean Curvature Surfaces to Overdetermined Problems. Okay, so the aim of this talk is to present some result from constant mean curvature surfaces and some result issued from the study of overdetermined elliptic problems and to see some relationship between them. Okay, so since it's not certain that all of you know what is mean curvature, I will start by definition of mean curvature. Okay, so suppose to have a surface sigma in R3. For example, like this, and P is a point on sigma, and N is the unit normal vector. Okay, what we do is we consider a family of planes passing through P and containing such a vector n. So I will sketch one of these planes here. Like this. So planes containing n, and I consider the curve gamma given by the intersection of sigma and a plane pi in this family. Suppose that this to be pi. Okay, what we get is a planar curve and of this planar curve I can compute the curvature. Okay, I can compute K curvature of gamma. Okay, and I repeat this process for any pi in the family of planes containing n. Okay, so I will get, for example, maybe I can use another color. I will get a family of curves on sigma passing through P. For each curve, for any gamma, I compute a curvature, K gamma. There will be one maximum value and a minimum value for this curvature. Okay, so max minimum of K gamma. I will denote, for example, the maximum by K1, the minimum by K2. This is what we call principal curvatures of sigma at P. So now what is the mean curvature at P? This is the average of these two numbers. Okay, this is why we use adjective mean. Okay, so in what follows we focus on surfaces for which the mean curvature is constant. Okay, okay, so let me mention one important result about constant mean curvature, which is due to Alexandrov. Alexandrov proved that if I take a compact embedded means with no self-intersections, hypersurface in Rn, then a surface like this is automatically a sphere, round sphere. There are no other surfaces. Okay. Okay, so oops. Maybe I can move this up. And this famous theorem here is being proved by a method which today is known as moving planes. And essentially, if such a surface is not a sphere, is an horrible shape like this, let's say, and I take a plane intersecting this strange object, now I take the piece of surface located on the right, and I take its reflection with respect to my plane. I get another piece of surface located somewhere here. Okay. Now I move this plane from the right to the left, and at a certain point I will touch the original surface, for example, here. And then I use a very famous tool by analysis, which is maximum principle. To say that the original surface and the reflection of this piece here have to be equal. Okay, so this proves that this strange object here has to be symmetric with respect to this plane. But I can repeat the process for any other planes. And I can prove that this object has infinitely many planes of symmetry, and as a result the surface has to be a sphere. Okay, this is the idea. Other results about constant mean curvature surfaces are concerning the non-compact ones. Okay? Non-compact. Okay, how a constant mean curvature surface which is non-compact look like? It looks like the following. Suppose that M is such a surface, then if I remove a ball of radius r with r big enough, so BR is a ball, BR, solid ball. What I see is that M minus PR has a finite number of components which are diffeomorphic to S1 cross R plus. S1 cross R plus is an half cylinder. Okay? very famous example. The catenoid. The catenoid is a constant mean curvature surface with h is 0. So in this case we have a minimal surface which looks like this. Now, if I follow this recipe, I remove a ball from the surface here. What I get is two non-compact stuffs which are diffeomorphic to an half cylinder. Okay. What about the case H non-zero? Okay, for certain reasons we don't consider H negative, we consider only H positive. A constant mean curvature with H positive looks like this. For example, the picture is not that nice. Okay, so if I remove the central block here, I see three objects diffeomorphic to an half cylinder. I forgot to say that this non-compact part is what we call ends of the surface. Okay. Okay. Okay, there are the following surprising results. So if I have a constant mean curvature surface with H positive, assume also it is embedded, then the number of ends cannot be 1. So or there are no ends and the surface is compact, or there are at least 2 ends. So this means no ends or at least 2. If you are in the second case, number of ends equal 2, then the surface is rotational. Surface, surface is rotational. There are no other constant mean curvature surfaces with 2 ends. Okay. So do you understand that in this case the surface is special and it has a name? Actually it has been discovered in the 19th century by Delaunay, and it looks like this. Okay, sorry if it's not exactly rotational, but okay. Okay. Okay, now the section of this talk focusing on surfaces is finished. Now I try to explain what is an overdetermined elliptic problem. An overdetermined elliptic problem is a system of an elliptic differential equation so for example something like this, where delta is the Laplacian and here we consider, okay, so we want to solve this on a domain omega, and we impose the Dirichlet condition on its boundary, but also the Neumann condition. Okay, so two boundary conditions. This is why we have overdetermined. Okay, in general, if we choose omega and we try to solve this problem, in general there is no solutions because the boundary conditions are incompatible. Okay. Okay, so the approach that is followed to study these things, so is not that one described 1 minute ago. So we don't try to solve it, we assume I forgot to do something. Assume that there exists mu and omega for which let's say assume exists omega for which star admits a solution which kind of information can we deduce about the shape of omega and the structure of U? Okay, the first result in this sense, in this direction, is the result by Serrin, who considered a simplified version of this. He considered this, Laplacian of U equal to -1, U equal to 0 on the boundary, derivative of u with respect to the normal vector constant. And surprisingly, he used the same technique of Alexandrov, which is a moving plane. Of course, an adaptation of his technique, planes. And he proved that omega, if we assume, like written there, that there exists a solution, omega has to be solid ball, and the function u has to be radial. Okay? What is the boundary of omega? Boundary of omega is a sphere. Okay? CMC. The r I use here is the distance from the center of the ball. Okay. Other persons generalize the result by serine, considering also minus f of u with certain hypotheses on f, and they prove the same statement. Okay. Okay, so serine considered only compact domains, but other persons studied non-compact domains. So in the case of compact domains, we have that the boundary is the unique compact CMC. In this case here, we expect to find a similar result. The boundary of domains for which a system like this is a solution probably will be a CMC again. Okay, so in the non-compact case, there are several authors who studied this. I will mention only oops. Probably for most of you, these names will be useless, but anyway, I'm obliged to say something. So they studied the system there. Okay, useless to copy again. Omega unbounded. One more, I think I forgot. The solution to a system like this has constant sign, which is important. So it can be supposed to be positive. Okay, so in this case, they prove the following. Suppose, for example, that omega is an epigraph. Omega equal epigraph. Epigraph means in 2 dimensions Okay, two dimension is this, is the region of the plane whose boundary is the graph of a function. In Rn I can write this. Oops. Bigger. Okay. And they proved that if on omega, like that, this can be solved, then the function f that we have there, this is a constant, and this means that omega is half space. Tell me if it's much technical or is okay? The level of difficulty? Okay, thanks. Observation. So, what is the boundary of omega? Boundary of omega is an hyperplane, and this is again a constant mean curvature surface. Okay, because it has mean curvature equal to 0. They also stated this conjecture. So now omega is not an epigraph, it is a generic unbounded domain. They said that the unique unbounded domains on which this system admits a solution are solid cylinders, oops, okay, solid cylinders, R spaces, Rn minus a ball, and case number 4, Rn minus a cylinder. Okay, cool. So in all of these 4 cases, boundary of omega is a CMC hypersurface. Okay, cool. Okay, so recently for n bigger than 3, n is the value of this number. It's been proved that this is false. Okay. Because there are domains like this. Domains whose boundary is, sorry if it's not nice. Oops. And this is the shape of the surface I sketched before. Instead, for n equal to 2, who proved this is Schlenk, Sigbaldi. And instead, for n equal to 2 is true. But in this case, there are some hypotheses on F. Some hypotheses on F. F is the function you have here. Okay, so how much time I have? 26 minutes. Okay, so you see, there is a certain similarity between results in constant mean curvature surfaces theory and these things. Now, what I will try to explain is a very precise. Okay, I can erase this. A very precise result proved by Frese. So far we have some, let's say, we see a similarity, but it's not, how to say, that precise. Instead, this guy proved that if we consider a special case of this system, which is this, so we have harmonic functions, U0 on the boundary, of course U positive, and du dm, let me write, okay, it's okay, constant on the boundary. And here we work in R2 only. So it's a very special result, but the result is very nice, in my opinion. Okay. Okay, so he proved that there exists a one-to-one correspondence, which is explicit, more or less, between two classes of objects. One domains omega satisfying that one. So these domains support an harmonic function, a positive harmonic function, plus an hypothesis about which I will not give any comment. Okay. Okay, let me write one. If I want to give the precise statement, I have to write one. Okay, so I will not say nothing about this. Domains omega such that du dn is more than 1. This is true on the boundary, and this is in the interior. Okay. 2. Complete embedded minimal surfaces. A minimal surface is a surface with h equal to 0. So it's a constant mean curvature, which are symmetric with respect to a plane, more precisely the horizontal one. Okay, I'll try to make some picture. Okay, example. Do you remember the catenoid? The catenoid is symmetric with respect to this plane here. Okay, so an example of minimal surfaces with satisfying this is the catenoid, and he proved that. Okay, preliminary remark. If I consider the intersection of M with x3 positive, so I am looking at this part of my surface. I have a graph on what? On this. Okay? You forget this part. This surface here is a graph on R2 minus a whole. And he proved that the unique domain omega, which is sent by this correspondence to the catenoid, is exactly this, and there are no others up to diffeomorphism. Domains with one hole, there is only this one, and the surface is the catenoid. Second thing he proved, if the number of holes is higher, they are like this. One, two, three, and so on. So this is something periodic. And you are thinking maybe, if you are not too much tired, what is the surface which is in correspondence, which is in one-to-one correspondence with this domain there? Okay, it's difficult to make the picture. The surface looks like, okay, the name is Scherk, singly periodic surface, and it looks like, I hope to be able to sketch the surface. So I have some sorry, small correction. Okay, imagine two sheets of papers like this, connected by a bridge. Okay? Now you replicate this block infinitely many times. So you have infinitely many bridges. And if you make a rotation, for me it's easier to sketch a picture in this way. If you sketch this picture horizontally, you see that this stuff there is a big graph on this domain. Okay. The surface will be like this. Sorry if it's not that precise. Okay? So we have half a surface above these planes and the remaining half below. How much time? 15 minutes. So maybe I can say you more. I've been faster than expected. Okay, so maybe one word about how this is proved. Okay, which I hope will also explain why this result cannot be proved, for example, in R and with n bigger or equal than 3. Okay, minimal surfaces in R3 are special. Why? Because we have a very powerful tool to construct them, which is the Weierstrass representation. Okay, what is the Weierstrass representation? Suppose you have a connected domain in C. Suppose you have a function g on omega, which is holomorphic. We suppose omega bounded to avoid any problems, but what I'm going to say can work also if omega is C bar minus a finite number of points. Okay. Holomorphic and a differential form holomorphic. Then if I use this formula, minus plus. If I use this formula here, xz is a minimal immersion. In other terms, xz is the parameterization of a minimal surface. Okay? Okay, so here you see there is omega, a domain. Here you have a formula to construct the surface. And what is the link between I erase, I'm sorry. The link between, I will not copy this because I don't need them anymore. What is the link between a minimal surface and harmonic functions? Is the following. The Gauss map of this surface here is harmonic. So you can construct from a surface an harmonic stuff. Well, this is the idea of the correspondence. Surface domain, surface solutions. Okay, I'll stop here. Thanks.